Or did you guys find this?
Did you find this in your packet? It's a big table where you already have the structural drawings. Alright, so if you feel, just give me like a 1 out of 10, who feels like they can predict molecular geometry or electron group geometry in the bonding course? What's a 1 out of 10 scale? Alright, I need everyone to participate in my survey at this point. Thank you. Alright, so I've got a lot of 2 hands up. Great. Go ahead and think we should feel here.
Oh, no, so we're seeing you guys about classes for next year. If you wouldn't mind handing those out, we'll see them one at a time. We're actually going to start with Ms. Khan's class first, so we won't be in here for maybe next 15 minutes or so.
Thank you. I just come see my class. Margaret, Jillian, Darcy, Daddy, Gigi, Kathy, here. Did any junior not get one? He's not here today, so he will advise you at another date. Yes.
Okay, guys, back to me. Back to me. Put this away from me so I know I have your undivided attention, okay? So they will call you out, but there are a couple things we're doing today. We're reviewing molecular geometry one more time. We're looking at how polarity, molecular polarity, plays into intermolecular forces. With me, ladies? Margaret and Jillian? Thanks. So we're looking at how polarity plays into intermolecular forces, and then you guys are teaching intermolecular forces today. Okay? So you're going to self-discover a little bit on making a good jigsaw assignment. That basically means that we are groups, and then you become an expert in your topic, and you come back and teach your group. And that's what this last part here is. I'd like to check over that textbook homework too, but I got to pass it back. All right, so looking on your charts, what's the first combination? How many ligands? So when it says shared pairs, it means 2 ligands. All right, so you can already see the structures as AX2, and it's linear. So I want you guys to draw the structure. Just give yourself a little, just a sketch. It doesn't have to be pretty. And let's talk about how this would impact polarity likely. So you have something going left and right. It's just a little bubble. You've got no lone pairs on the central atom. If X and X were the same exact atom, what would the polarity be? Polar, nonpolar? Nonpolar, because there should be no distortion of electrical charge. It should be equally distributed across the molecule. The next one, give yourself a quick sketch. Doesn't have to be beautiful. So I'm going to do this from memory. I think it's just AX3. Okay, so what is that shape? Try not to look at that column where the shapes are so you can have a chance to try it out. Trigonal what? Planar, so it's a flat plane. There are no lone pairs on this structure. So it is equally distributed in a 2D shape, up and kind of down to the left and down to the right. So that's going to give us a trigonal planar, which is 120 degrees. If all of those are the same atom, if X is all the same atom, polar, nonpolar. Nonpolar again. And these are this is the molecular polarity, right? So the molecular polarity comes into play once you've considered the bonds themselves, like the electronegativity differences, and how they're arranged in space being the geometry. What would be the electron group geometry for this one? Because this is molecular geometry. What would be the electron group geometry for this one? Loud and proud. Linear again, because there's no electron pairs, so the electron group geometry is the same as the molecular geometry. What would be the electron group geometry for AX3? Say again? Loud and proud, guys. Trigonal, planar, because there's no electron group or electron groups to cause any distortion, so therefore it's the same. Next one, you got what? One lone pair, right? So what has happened to the molecular geometry? It's gone from trigonal planar to bent. Okay, but in terms of the shape, that's the molecular geometry. We're talking about how the shape has changed with the atomic interactions or the atomic structure. So we're going to, and remember I told you angular was kind of an old term. We use the word bent now, but it has definitely a bent shape. Why is it bent now, though? Right, there's a lot of repulsion going on from this big electron pair, so it's causing it to be maybe even a harsher angle than 120. That's why it says a little less than 120 on that particular row. So maybe 120 could be a little less than 120. It really depends on what these X's are. What kind of polarity are we dealing with here? Definitely polar, with no question, because we have a bent structure, an unequal distribution of electrons. What is the electron group geometry here? Trigonal, planar, right? It's the same as the above, because it's just counting everything equally. Lone pairs are equivalent to bonded pairs. The 4 ligand one shape, tetrahedral bond angle, loud and proud, 1 to 9.5, and once you start changing ligands for lone pairs, the bond angle gets down or lower and lower and lower. But we start off with 1 to 9.5. If X's were all the same, polarity, non-polar. Good. So that's going to give us a chance to notice that that arrangement in space can give us equal distribution in a sphere with having all the same ligand. If you have different ligands, it gets more complicated. Most of the time, if you have different ligands, you're going to have a situation where it's going to be polar in some fashion. When you drop a little ligand, you add a lone pair. What's the shape? Question, JT?
I was just going to ask, so is the bond angle the same for all shapes? Like is the bond angle always 1 to 9.5 for tetrahedral?
Yes, it's the bond angle for 4 ligands on that tetrahedral structure is 1 to 9.5. That means 4 ligands and 0 lone pair. Because once you add lone pairs, you're going to start to have some distortion. But yeah, that's the bond angle there, everywhere. Okay. All right. So when I drop off a ligand, I call it, and instead replace it with a lone pair. What do I create? Trigonal pyramidal, right? So the pyramid aspect is due to the fact that there's repulsion happening from the lone pair. It's pushing down, pushing those ligands even farther away, but yet closer together. So what's the bond angle here? We go from 1 to 9.5 to 107, right? So we're dropping about 2.5 degrees. Now this is all approximate. In real life, the size of the X's, the size of the ligands can cause a little bit more distortion, but we do have a kind of general rule of thumb. It's 107, and then would that be considered polar or non-polar? Loud and proud. Polar. There's a huge honking lone pair up there that's not countered in any way on the underside, so this would be a polar molecule. Okay, keep moving. Drop off another ligand, give yourself a lone pair. What is your shape? Your shape is what? Bent, okay? And if you, so this would be, a real life example of this one would be what? H2O, right? Water's got 2 ligands and 2 lone pairs, and so we already know that is definitely not going to be canceling each other out, because the bent shape here has 2 lone pairs on the, let's say, kind of here on the back side. And what would that polarity be? Definitely polar. And since we have more lone pairs, we have more repulsion. What's this bond angle? 104.5. So we've dropped down another 2.5 degrees. What was I asking here? Oh, so all of these are essentially the same. It's just ligand or lone pair in the place. So what are all of these in terms of electron group geometry? Tetrahedral. They are technically all tetrahedral in electron group geometry because we count ligands and lone pairs the same. But in molecular group geometry, they have fancy names. Oh, sorry, and this last one. This one too. Okay, so this is the last one where you guys have one like this in your lab, HCl or HF, something like that. So you had your, in this case, A is our central atom. A or X could be, though, it doesn't really matter. So in this case, we've got 3 lone pairs, 1 true ligand, so our angle is 180 degrees. It's linear. What would you guys consider the polarity to be? Say again? Likely polar, and that's probably due to the fact that A versus X, there's a big difference, or at least a moderate difference in electronegativity, because in this case you can definitely see one of these is able to hold on to more electrons, and that's likely because X is probably maybe hydrogen, because it's not going to be able to hold on to more than one pair, so that bonded pair. So a large change or a large difference in electronegativity will cause it to be polar. Don't look, sorry I didn't cover this one. Okay. Keep going, so try not to look at the shapes on your own. 5 ligands, no lone pair shape. Visualize. Trigonal, 5 pyramidal, right? There's 2 pyramids, one on top, one on bottom. In the equatorial plane, how many ligands are there? 3. Right, equatorial, there are 3 ligands. On the axial plane, how many are there? 2, so that's why you have 2 pyramids there. So, well, there's a nice, no, actually, I think I have to draw that one. Well, there's a nice drawing right here. You can see the A's of the central atom, and you have this little kind of triangle shape in the middle, and then you've got a diamond or a pyramid on top and bottom. A little hard to see. I'm going to stop drawing on top of it because you can see it better without my drawing superimposed. And then on the bond angles, the equatorial to axial bond angle is what? 90. So the equatorial to the axial bond angle is 90. And then the equatorial to equatorial is what? 120, because you have a 360 divided by 3 is 120. Polarity? Likely nonpolar. When all of our assumptions so far have been that X is the same atom, right? So if we have different atoms, we could have a polar molecule. Drop off one of those ligands and give yourself a lone pair. What's the shape? Say again? Seesaw, right? So we have 4 ligands there. 2 kind of take on like this appearance, and 2 are on the axial plane. So which ligand did we take off to replace with a lone pair? Do we take an axial ligand or an equatorial ligand? Equatorial. Why is that beneficial? Why is that better? Okay, because they have a 120 angle, so they have more space. So if you can think about how it comes from here and then you go down, you can actually see the changes over time. So we have seesaw. Okay, so we keep our axial because they're going to have to be ligands. We keep 2 of our ligands in our equatorial position, and we add a lone pair on the equatorial position. The angles still kind of remain the same. Definitely the 90 degree stays the same. It can't really shift too much. Because there's a honkin' lone pair back here, we do say it's 120. It could be a little less than 120 because it could repel, so it could cause these angles to be pushed together just a little bit more, but they don't get too specific on the AP exam. This is fine. So seesaw, in this case, polar, non-polar? Definitely polar. We have a huge honkin' lone pair that's not countered or negated in any way or form on the opposite side. Okay, so as we go farther, we drop off another ligand, we add a lone pair. Where's it going? Axial or equatorial? Equatorial again, because it's got the most space to play. What's that shape? T shape, because we now have 3 ligands, 2 in the axial, 1 in the equatorial, 2 lone pairs on the equatorial. We call this bond angle just the bond to bond angle, which is why this one only says 90. But we know, like in our lab, when we're looking at repulsive units, we know that there's an angle between the axial and this bond, or this lone pair. What's that angle there? 90, right? So that's super repulsive. Lone pair to axial, or to bonded pair. What's the bond angle between these 2 lone pairs? Approximately 120. There's not much there. I mean, there's some repulsion always, but nothing that we were going to calculate within our repulsive units. And then what's the bond angle between this axial bond in this lone pair? It is 90, because it looks, the shape, the structure looks different, but we know it's equatorial and axial, so it's going to be 90 all the way around. Polar and nonpolar, definitely polar. The lone pairs are not countered in any way or form. Keep going. What's the drop off another ligand and add a lone pair? Where's it going? Equatorial again, right? So what's our shape? Linear is just a different kind of linear, right? Because the axial plane is staying where it is because all these lone pairs are taking the central position, and the linear structure remains. So the angle that it's speaking of here is between the x and the x, but we know that there's more angles that you could talk about between x and this, the bonded pair and the lone pair. What's this angle here? 90, but what are the angles between all the lone pairs? Approximately 120. Polar or nonpolar? Nonpolar, because we have a equal distribution of charge. We have, if this were a polar covalent bond, A to X, it would be pointing its dipole moment up, and A to X would be pointing its dipole moment down. So what would those two dipole moments do with each other? Cancel. And then we have a lone pair out, out, and out. And if I kind of look at them equally, because they are all just a lone pair, they also cancel each other out. So in the end, we have no polar moments at all. Keep going, drop off. Actually, no, I don't think this one has this. Okay. 6 ligands, no lone pairs. Square bipyramidal, also known as octahedral. It's just a lot of times we see the square, we say square, we see 2 pyramids, we say bipyramidal. I think that one's just a little bit more natural coming off the tongue. And then there's a 90-degree angle everywhere. You don't have any trigonal aspects, so therefore there's no 120s. Polar or nonpolar? Say again? Nonpolar, because there's equal distribution around. Drop off a ligand, add a lone pair. Where would that go? Doesn't matter in this case, right? Everybody's at 90 to each other. I see it better to drop off the axial. So if I drop off the bottom axes, what shape do I see? Square pyramid, right? So I don't have that bottom pyramid anymore. So I have a square pyramid. And we still have all the same bond angles present. It's just now we have a little bit more repulsion going on the bottom. This lone pair that's here, it wants to repel. It wants to push that square away. But what would happen if it pushed all these x's in the equatorial region up? The angle here would be what? Less than 90. Ain't no way. Like they can't get much closer than 90. There's still repulsion even though they are bonded. So that's why this is still going to be called 90, 90, 90 all the way around. Polar or nonpolar? Polar, because you have a big lone pair in the bottom. That's not countered. All right, so if this were the placement for this current lone pair, where would I replace and put another lone pair? On the opposite side, on the opposite axial region. So what's that new shape? Square, planar, because it's a flat square. And there we go. Polar or nonpolar? Say again? Nonpolar. Yay! Are you feeling a little bit better with shapes? Sometimes bond angles can kick us, but the seesaw and the T-shape are only weirdos. What was the electron group geometry for all of these? Octahedral or square bipyramidal. And then, I think I already forget that one. Well, what was the electron group geometry for all of those? Electron group geometry for all those? Trigonal, bipyramidal, right? Because there's 5 effective domains or 5 electron domains. All right, go to my website, go for under where it says classwork, under homework for today. Eventually they will start calling you guys out, so I'm going to try to assign this to you, show you this first. I'm under honors chem, if you guys wish. So under March 5th, this is classwork, IMF jigsaw, and then you guys can see tonight, you just have reading, NMSI reading. I put the weird PDF link from Google, the Cami one that makes you log in, and I put the actual NMSI one, so you guys have access to either there. So when you click on that link, this will pull up for you, and it gives you a quick explanation of what you're doing in expert groups, and then what the basis of intermolecular forces are. But what I'm going to go ahead and do is just assign you a group. So you'll be assigned to group 1 through 5, London dispersion, dipole, induced dipole forces, also known as dipole-induced dipole, or ion-induced dipole. I do have a separate group out there for number 4 is a different group. Ion dipole, and then lastly, hydrogen bonding. You've heard of 3 of these, maybe 4 of these. The other ones are actually kind of self-explanatory if you think about what it's saying in this title. But within your group, you will be drawing an illustration. Of course, these are going to be images that you guys can find online. You don't have to draw it right now. Use appropriate chemical structures. Try to include some real, like, simple ones and then some more complex ones. It's not like humongous organic molecules, but just a little more complex than water. Okay. What type of attraction is the basis? Is your attraction strong, weak, or intermediate? Why? What types of common substances are held together by your intermolecular force? How does your intermolecular force directly affect the physical properties, aka melting point or boiling point? So this is kind of the basis of what you're looking for. If you're assigned the London dispersion forces group, you just have a keyword called polarizability. That would be important to include in your explanation. Okay. So what I'm looking for in about 20 to 25 minutes is a really short presentation, a Google Slides that's going to include this information, and that Google Slides will be shared by everyone in your group. Once you guys have crafted it and you have a clear understanding of your IMF, you break out into smaller group or into other groups where there's one representative from each of these groups above. Okay? And then you do about a 5-minute spiel on your topic. Does that make sense? You have to be the expert of your topic because you are coming out of your expert groups into smaller groups that are more diverse. Got it? I'm just going to number you guys off, okay? Here we go, because you'll be with different groups throughout the day. So just, numbers are here, okay? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. Okay? Ones, who's the first one? William, okay, gather. Who's the 2? Gigi, gather. Who's the 3? Margaret, gather. 4's with Julian, gather. Megan, you're 5, gather. You guys see space? And then you guys need to share that presentation with me immediately, okay? Space in here first, yeah. Share that presentation with me. There's plenty of lab space if you want, but it's fine. CJ, you can grab a stool. Grab a stool. Here. That's cool. So I will point you to the resources that are below. The resources appropriate for each group. The IMFs reading 1 is really good. Video 1 is really good. Some of those are the more basic IMFs like you learned in honors chem. So if you're LDF, hydrogen bonding, or dipole, you have a lot of information there. I've tried to put down some other resources here. You also are smart cookies and you are able to surf the web just fine. On your own time, you'll have to look over each of these 5 presentations, preferably before tomorrow, so you can see what we discussed today in class.